So let's review what we know about collision theory and review some of the formulas that we're expected to use that are related to this idea. So I'm sketching out, overshot there, a collision tube, okay, and this is the path swept out by a moving particle. And that we'll put that particle right here. We'll color it in. I'm going to make it about that size relative to the cross-sectional area of the collision tube. So that particle is the one that is moving. And it's moving in that direction. And particles move in straight line paths. And they're not influenced by the particles around them, but they do collide with them if they're in their path. And if a particle is outside of the collision tube as we've drawn it, then it's not going to hit it. This would be a miss. But if it's within the space marked as the collision tube, then it will be a hit. And it doesn't have to be completely inside, but a particle sitting here would definitely be hit. So we have to think of these as stationary and this one moving in our treatment. So here's my particle moving at a mean speed, and it will hit this particle and it will miss this particle. What is the length of the tube? Something we need to be able to do. What is the length of this collision tube? Well, the basic idea tells you that the distance is equal to speed times a time period. So, for example, 5 meters per second times an amount of time in seconds, cancel out the seconds, and I get a distance in meters. So the same idea applies here. And the speed the particle is going is a mean speed. And so the distance is the length of the tube, and that is the distance that this particle will travel if it's traveling at a mean speed for a period of time, delta t. Remember to use small t for time because capital T is temperature. And we're really unforgiving about that. The formula for this, 8R, gas constant R, capital T for temperature, over pi, capital M for a molar mass. All of that to the square root 1/2, or to the exponent 1/2, which is the square root, times delta T. And that will be the length of the tube. So 8R, 8.3145 joule per k mole. That joule will have to be written in its component SI units, and remember that a joule is a kilogram meters squared per second squared. This relationship is always given on a test. Temperature in Kelvin, pi is a number, and this is kilograms per mole of that molecule. So if it's H2, twice the molar mass of atomic hydrogen, for example. So don't forget to account for any molecular formula, but this is the molar mass in kilograms per mole. So again, all the units here are going to remind you of what the units should be, because you want them to cancel, and your time will be in seconds, and there's a seconds, of course, in my joule. And the units should all cancel except for a meter, and the length of the tube should be reported in meters. Given that, what is the volume of the tube? How would you find the volume of the tube? Well, again, volume should be cross-sectional area of the tube multiplied by its length. So we just calculated the length of the tube up here, and we need a cross-sectional area. Let's move this up. Not too far, I still want to keep this in view. So my radius of the tube, and I'll write it down here, the radius of the tube is equal to the diameter of the particle. Okay? The radius of the tube is the diameter of the particle. The cross-sectional area of this, it's pi r squared. The r is the radius of the tube. So the cross-sectional area is equal to pi r squared, where this is the radius of the tube. However, we have the properties of the gas particle, not of the tube. And since the radius of the collision tube is equal to the diameter of the particle, we write that the area is equal to pi d squared, where this is the diameter, of the gas particle. And that's something that I can look up in a table. Okay, so the formula looks a little bit off for the area because it should be pi r squared when you look at it just for face value. But of course we understand why it's written as pi d squared, because it's the diameter of the gas particle, which is equal to the radius of the tube. So back to the volume then. The volume is this guy, pi d squared, then multiplied by the length, which we just found above, and that was the mean speed times delta t. And sometimes this is given for a particle, right? Because it's just a property of a particle. And pi d squared is sometimes known and given as sigma. And sigma is the cross-sectional, sigma is the collision area. Cross-sectional collision area. So sigma might be given for the particle, or the diameter of the particle might be given. So either way, if you're given sigma, you'll recognize it because it'll be in square meters. Small number probably won't be in square meters. It'll probably be in something more to the scale, like picometers. And of course, if it's the diameter of the molecule, that'll be given just in meters or picometers. This in meters squared or picometers squared. Okay, or some unit of distance squared, some unit of distance. So there we go. And that is the volume of the tube. And so this in say whatever it is, a square meter, a square picometer, but you would convert it to square meters. And then this is meters per second. Okay, so let's just jot this down. That would be square meters, or even if it was a square picometer, you would convert it to square meters within the calculation expression. And then your speed is meters per second, your time is in seconds, and you see that you end up with a unit of volume. Perfect. Okay, and try to remember to report your answers in scientific notation, and that really encourages you to use the right number of significant figures. That's what I like to do. Okay, so we have our length of the tube, the volume of the tube. What next? The mean free path. Very important. Mean free path. So let's move this up. The mean free path has a variable lambda. And lambda is a distance, and it's the distance the particle travels between hits. And for this one, I'm just going to give you the formula and not actually derive it. We derived it in lecture. And we got this. Let's just do out the units for this. So K is a Boltzmann constant. And the Boltzmann constant is, it's given always in a test situation, but its units are joule per Kelvin. So joule per Kelvin. And I know that I'll have to convert my joule unit to its component SI units. So I know that a joule is a kilogram meters squared per second squared. And then that's all multiplied by temperature, which would be in Kelvin. And then it's divided by sigma, which should be in square meters, and divided by pressure, which will most likely be, well, in any unit, you're going to convert it to a Pascal. So if it's torr or bar or atmosphere, PSI, millimeters mercury, convert it to a Pascal. And then in the expression, like we're doing here, convert your Pascal to its component SI unit. So a Pascal is a kilogram per meter second squared. I always have to think. A Pascal is a kilogram over meter second squared, whereas a joule is a kilogram meter squared per second squared. Okay, so there you are. And I'm hoping that all of these units are going to cancel and just give me a unit of distance, meter. So joule, joule, Kelvin, Kelvin, kilogram, meters squared, Pascal, second squared, and there's my meter. Perfect. So you know you're well on your way when this happens and you're doing the solution. And it's really lovely if you do this, because it really helps the person marking to say, oh yeah, there we go, everything is there, everything cancels, here we go. The marker will still go through and make sure that this makes sense, and the calculations and the cancellations make sense. Okay, so that's the distance the particle travels between collisions, or the mean free path. And then our last variable that we should know is a small case z, and that's our collision frequency. And a collision frequency would be equal to the number of so-called hits, like we sketched in the collision tube, per unit time. Per unit time. And let's think about the tube for a second. How do I calculate the number of hits? Well, any particle that was in the tube was going to get hit. So actually the number of hits is really the number of particles in the tube, in the collision tube, in that volume that we just calculated. And my unit of time, and I used it before, is just a delta t. It's that snapshot, that time period, because this is just going on continuously. And the number of particles in the volume would be equal to something called the number density, this fancy n. The fancy n is equal to, well, it's the number density, so it is just like a density is a mass over volume, a number density is the number of particles per volume. So that if I just want the number of particles, I take that number of particles per volume and then multiply it by the volume, and that'll just give me a number, delta T on the bottom. So what do I have for Z? So far, I have this fancy N number density, and the volume we calculated up above. We represented it as sigma, and then a mean speed. But because this is a collision between two particles, it's a mean relative speed. And my two particles colliding are the same, so my relative mean speed is equal to root 2 multiplied by the mean speed. What was the formula? Times delta T. So you can look up above where we saw that the volume of the tube was equal to sigma, the mean speed, times delta T. So here I have sigma mean relative speed, delta T. And again, the mean relative speed is root 2 times the mean speed. And don't forget, this was all over delta T. Great, because now this cancels and I don't have to worry about that. And so now my collision frequency is equal to this sigma mean relative speed. Not ready to plug into to solve yet because of this guy right here, the number density. And let me just grab another sheet of paper to show you how I can state that a little differently. What is, so a little aside here, what is that number density? That number density, as we said, is equal to the total number of particles. See how my n is just a capital N? That's my total number of particles divided by the volume. But remember, this is for a perfect gas. And so I know that PV is equal to nRT. And I can rearrange for volume as nRT over pressure. And so this number density is equal to, write that out, total number of particles over nRT over V. And this total number of particles would be equal to the number of moles, small n, multiplied by Avogadro's number, all over nRT over P. And that allows me to cancel number of moles. Now my number density is equal to Avogadro's number. I'm going to bring pressure up here and divide that by RT. Okay. Now right away I'm going to point out that I have this R value here. And R is equal to Boltzmann constant times Avogadro's number. Remember that really that the gas constant R and Avogadro's number are kind of the same thing except different by scale. So this is joule per Kelvin and this is joule per K mole. That is my per mole. So I want to replace this R with Avogadro's number times K, and that'll really help out. So now I've got N equal to N Avogadro's number times pressure divided by Boltzmann constant N Avogadro times D. So now that goes, and now I see that this number density is just simply equal to the pressure of the gas over Boltzmann's K times temperature. Love it. So now we go back to, as I said, let's recall that we were trying to find out a formula for the collision frequency, and we left it at this number density sigma relative mean speed. So now I can take this and substitute it in for my number density, and I get P sigma mean relative speed over Avogadro's number times temperature. And this relative mean speed, where the two particles are the same, so I don't have a mixture of gases, so that's fine, is square root of 2 multiplied by mean speed. So that's it. Pressure, you want it in pascals, and then open up that Pascal unit to your SI units. This will be in square meters. This is meters per second. This is joule per Kelvin, and then you want to convert that joule to just its SI units. And temperature is in Kelvin. So everything here is going to cancel and give you units of, should be seconds to the minus 1. Right? Let's do this and make sure, because it's a frequency, right? So pressure is in Pascal. I'm just doing units here. And I want to open up the Pascal unit to its SI units. And a Pascal is a kilogram per meter second squared. So Pascal is a kilogram per meter second squared. Okay, and then I've got my sigma, which is going to be in meters squared, and then my speed, which will be meters per second, and then this is joule per Kelvin, but a joule, one joule is a kilogram meters squared per second squared, and then I multiply that by Kelvin. So Pascal, Pascal, meter, meter, and joule, joule. Oh, I messed up. Right, so we said the units for the collision frequency should be seconds to the minus 1. Let's just verify that. So the formula is P sigma relative mean speed all over Boltzmann K times the temperature, where the mean relative speed for pure gas is simply equal to root 2 multiplied by the mean speed. And that mean speed is, we saw earlier, equal to the square root of 8 RT over pi big M. And its units would be meters per second. Okay, so verifying here that the units should be seconds to the minus 1, and then it actually turns out that way. My pressure would be in Pascal, and I would convert my Pascal. 1 Pascal is a kilogram per meter second squared, so 1 Pascal is a kilogram per meter second squared, times my sigma, which is in square meters, times my mean relative speed, or root 2 times the mean speed. In any event, that's going to be meters per second. Then divide by Boltzmann constant, which has units of joule per Kelvin. I'm on the denominator here, so that's why it's going to be written as joule per Kelvin this way. And my joule needs to be broken up into its SI units. So 1 joule is a kilogram meter squared per second squared. So a kilogram meter squared per second squared. And then I'm also dividing by temperature in Kelvin, so 1 over Kelvin. So let's go through and see if everything cancels. Pascal, Pascal, and kilogram, kilogram. Let's see, joule, joule, Kelvin, Kelvin, second squared, meters, meters, meters squared, and the only thing I'm left with besides that number 1 is seconds on the denominator, and so my units are indeed seconds to the -1. Great. Finally, finally are the formulas for the different sorts of different speeds that we have, our different benchmark speeds. And we have the most probable, we have the mean, and we have the mean relative, and we have the root mean square speed. So we want to look those up in our notes and make sure that we can identify all of these. We don't want to memorize them, we just want to recognize them. This one is 2 RT over big M square root. So R is the 8.3145 joule per k mole, and write your joule as a kilogram meter squared per second squared. T is in Kelvin, and this is kilograms per mole. Your units overall should be meters per second. Your mean speed is 8 RT over pi big M, again, square root. Now for both of these formulas, instead of R, you could have the Boltzmann constant K, but in that case, you would be dealing with a small m, and it would be the mass of a single particle instead of the molar mass. The relative speed is 8 RT over pi mu all to the 1/2, where mu is my reduced mass, and it is the product of big M A M B over M A plus M B, where A and B are my two types of gas particles. Now if I'm talking about a pure gas, then my mean relative speed is simply equal to, in that case, the square root of 2 multiplied by the mean speed, this guy here. And finally, my root mean square speed, is, I don't have the formula for that at my fingertips, so we'll just leave that one for you to look up. I can't think of it on the top of my head. Darn. Yeah, so finally the root mean square speed right here is equal to 3RT over capital M. And once again, you might see a formula with the Boltzmann constant K instead of R, in which case it would be 3kT over small m mass per particle. But either way, this will be in kilograms units for the mass. So as it's written here, 3RT over M, 3 just a number, R 8.3145 joule per K mole. Write your joule in SI units. Breakdown, which we've done a few times now. And temperature is in Kelvin, capital M, molar mass, kilograms per mole. And take the square root and you'll have units of meters per second. So we want to recognize each of these formulas. We want to know when to use them. And I'll just, as a final note on here, sketch for you what these benchmark speeds look like if we were to plot the speed and then the fraction of molecules at that particular speed. We would have this typical distribution like so, and we have a most probable, and next to that the second benchmark would be the mean, and next to that the highest one is the root mean square speed. So you could label those if asked. All right.